Alright, today we're going to be talking about permutations in probability. And first we're just going to start with a little review of the fundamental counting principle. And again, you can just recall here how we did this. And basically we just multiply in compound probability the number of possibilities of each experiment together. So here, if we have a license plate consisting of 2 letters followed by 3 digits, we want to start off by just setting up the places we could have. So we have 2 letters here, followed by 3 digits. Now, in our first example, repetition of letters and digits is permitted. Okay, so there are 26 letters in the alphabet, so we have 26 options here, and we can repeat them all, so we still have 26 options here. And there's the 10 digits, 0 through 9. And here we have 10. So again, we want to multiply all these together. And we have a total of 676,000 different license plates we can make. Now you recall, if the repetition of letters and digits is not permitted, then the number is going to go down 1 for each letter or digit we use. So again, we have 2 letters, 3 digits. There's still 26 options for our first one. Now it's going to go down to 25, okay, because we used one of the letters here. For the digits, we start with 10 digits, and we use 1, so it goes down to 9, and then we use another one, so the possibilities go down to 8. And so again, we want to multiply all these together. And as can be expected, we're going to have fewer possibilities this time. 468,000 license plate. In our next example, we have even more stipulations. So we have 2 letters followed by 3 digits. And it says the first letter must be a vowel, A, E, I, O, or U. So that means there's only 5 possibilities for our first letter. Now for the second letter, repetition is not permitted. So whichever vowel we used here can't be used in our second letter. And so now there's only 25 letters remaining in the alphabet. Now the first digit cannot be a 0. So that's going to mean we only have 9 choices for our first digit, the numbers 1 through 9. Now we assume we use one of those and we can't use it again. So now we don't have that one number, but now we do have the 0 available. So we're back up to 9 options. We use a letter and we're down to 8. So when we multiply across, we get 81,000 license plates. Now looking at our next example, this is talking about the different ways to arrange a specific number of items. Now you'll notice here we have 5 different Mickey Mantle cards. So it's important that every card is different. Okay, so we want to place the 5 cards in a straight row. So we still set up our places. So we have 5 spots for the 5 cards. We just ask ourselves, how many cards could go in the first position? Okay, well there's no stipulation, so any of the 5 cards could go there. But once we put a card there, we obviously can't put it in the second spot. So now there's only 4 cards available, and once we use that card, then there's only 3 cards, 2 cards, and then 1 card. So we multiply our possibilities together. And we have 120 different arrangements of the 5 Mickey Mantle cards. Now, if we want to put the rookie card in the middle, okay, adds a stipulation, how many arrangements can we do? So we still have 5 cards, but notice a specific card, the rookie card, must go in the middle. So there's the one rookie card that has to go there. And so you start off with that stipulation. Now you come back over, it doesn't matter the order of the rest of the cards. So since we used one of the cards, there are 4 cards left to occupy the first position. And then we use it, and then 3 cards, 2 cards, and 1 card. And when we multiply straight across, now we only have 24 possible arrangements. Okay, so that's just a little more on fundamental counting principle, expand on what we've already done. Now we're really going to get into the heart of what we want to talk about today, and it's something called a permutation. Kind of a funny word, but all it means is any ordered arrangement of a given set of objects. Okay, so it's an ordered arrangement. When we do this, we assume repetition is not permitted, just like we were doing in the above examples. So if we have the 3 objects, a happy face, a heart, and a moon, there are 3 different objects, and we want to see how many permutations there are for these 3 figures. So basically, we want to put these in all the different orders that we could see it. So 1, we could see it in the order that it is. Now we can also start off with a happy face and switch the heart and the moon around. Okay, so those are all the possibilities when you start with a happy face. It's kind of like writing the sample space here. So we're going to do, starting off with the heart. And we could do happy face, then the moon. We could start with the heart, then the moon, and the happy face. So those are all the ones that begin with the heart. And now we'll do the ones that begin with the moon. So we could do moon, happy face, heart. Or we could do moon, heart, happy face. So you can see here that there's a total of 6 permutations. Now if we think about this in terms of the fundamental counting principle, we really have 3 objects that we're going to be arranging. And we think for the first object, there are 3 possibilities: the happy face, the heart, and the moon. Now as we use that object, it's no longer available. Okay, that's the repetition is not permitted. So then there's only 2 objects left for your second possibility. And once you determine which one that is, there's only 1 left for the final one. And so we can see our 6 permutations can be found using the fundamental counting principle. So what we're going to talk about now is something called a factorial. Okay, and here's your equation if you're into equations. But let me just show you what that means. The factorial symbol is an exclamation point. Okay, what it means is you start with the number 5, and then you multiply by each smaller integer all the way down until 1. So this is going to be 5 times 4 times 3 times 2 times 1. So that's how you expand a factorial. It's a very short notation there. And we can do this in our calculator. We would see 120. For 3 factorial, you guessed it, 3 times 2 times 1, which is 6. So notice this example could have also been used up here to represent 3 factorial. Now 11 factorial, that's getting kind of long. And so we can actually use our calculators to make this a little bit faster. And what we want to do is use math, PRB, which stands for probability, and then find the factorial symbol. Okay, so watch in the calculator here. You want to push math. Scroll over to PRB. And all of this stuff deals with probability. And we want to go down to number 4. And that's your exclamation point. Now you can see when it puts it in, it's going to put it after whatever was there before. And so we need to make sure we put our number in first. So let's clear this. Let's try it again. 11 factorial, so it's under math, PRB, and number 4. So you can either push number 4 or scroll down and hit enter. Now we see 11 factorial, and we get a final answer. Oh, it's pretty big. So 39916,800. It's 39,916,800. So, how can we use this to answer our fundamental counting principle questions? It says, how many ways can 8 different books be arranged on a shelf? So it's asking for the number of permutations. Okay, now there's nothing special about this. We have 8 books and they are different. And so simply we can write this as 8 factorial. So no longer do we necessarily have to do these placeholders and then the fundamental counting principle. We can go straight to 8 factorial. So try it again in your calculator. So 8, math, PRB, and then 4, and enter. So here we have 40,320 possibilities. Another example, in how many ways can you arrange the diamonds in a deck of cards? So we think diamonds now, and there are how many diamonds? 13. So this is just 13 factorial. So we type in 13, math, PRB, and then the exclamation point. It's a very large number here. It's actually 6,227,020,800. Okay, now our examples so far have been dealing with when you're using all the items for a specific situation. Okay, so like the last one was all the diamonds in a deck of cards. Our next example now is we're going to be selecting only a few items out of a larger set. So here we have the 5 letters, P, Q, R, S, T. And how many distinct ways can 3 letters be selected and arranged if repetition is not allowed? So we're going to use our fundamental counting principle here to answer this question. So now we only want 3 letters. Okay, and for the first letter it can be any one of the 5 because there were 5 letters to start with. And then 4 and 3. And so this should be a review for you, and we get a total of 60 ways. So what we're going to do now is define this in terms of permutations. So you'll notice it's almost 5 factorial, but it just gets cut short. We don't have times 2 times 1, and the reason is we only wanted 3 letters, not all 5. So the way in math that we write this okay, of selecting 3 out of 5 is like this. So it's going to be 5p3. And we read the number of permutations of 5 items taken 3 at a time. So what this means is when we set up the fundamental counting principle, okay, that 3 means we have 3 spots. The 5 means that's the number we actually start with because there were 5 possibilities. So you get 5 times 4 times 3. Got it? So the 3 is the number of slots. The 5 is the number we start with. So you can see here that 5p3 is 5 times 4 times 3, which is our 60. Okay, so we want to write the following permutations that are in the form NPR. Okay, so for example A, we have 7p4. It means we have 7 objects and we're taking 4 of them, meaning we have 4 slots, 1, 2, 3, 4, and we start with the number 7. So 7 times 6 times 5 times 4. This gives us 840. Okay, so 9p3. How many slots do we have? I'm going to write it down. 3 slots. And what number do we start with? The number 9. So 9 times 8 times 7. And then we'll use a calculator to get this. Turns out to be 504. Try 10p5 on your own. And check out your answer. We have 5 slots, starting with 10, 10, 9, 8, 7, 6. Multiply them together, you get 30,240. Okay. We're not going to worry about this part right here. So, when we're doing this, there's actually a formula that we can use right here, which is n factorial over n minus r factorial. And, you know, it works, but I think thinking about it like this is probably a little bit easier than using the formula. Now, it turns out you can also use your calculator to do this. Okay, so let me show you how to do that now. And let's try it with 7p4. So in your calculator, you want to just start off by pushing the number 7. And we're going to go back to the probability menu. Okay, so hit the math, go over to PRB, and then you can see right here NPR, and that's permutations. So we go ahead and select NPR. And now we want to put how many items we're choosing, which is 4. So 7 NPR4, and we hit enter, and you'll notice we do get 840. Okay, so feel free to use your calculator when doing this, but it's also good to know exactly what this means so that you could find it even if you didn't have your fancy calculator here. Alright, so let's see how we can use this to answer some problems. It says you're among 8 people forming a club. You decide to randomly select a president, a vice president, and a secretary. How many permutations of officers are possible? Now, it's very important to note that a president, a vice president, and a secretary are all different jobs. So because they are different jobs, we know this is permutations and order matters. Okay, so basically if one of these 8 people gets chosen to be president, Okay, they can't be chosen to be vice president or the secretary. So it does matter what order you're chosen in. Okay, so we have 3 different or unique officers. So here's how we set this up using permutations. We have a total of 8 people, and we want the number of permutations if we choose 3 of the unique items. So again, let's go ahead and let's write this one out. So we have 1, 2, 3 spots. Start with the number 8, then 7, then 6. Okay. And this gives us 336 ways to choose a president, vice president, and secretary. All right, in our next example, an Adidas warehouse has 10 different styles of shoes. They wish to send a different shoe to each of 6 different stores. So how many ways can the shoes be distributed? Okay, well, we're choosing out of 10 shoes. And this is going to be permutations because the shoes are different and they're going to different stores. And we're going to 6 different stores here. So we get 10p6. Let's use our calculator for this one. So we have 10, math, PRB, PRB, and then NPR, and then 6. Hit enter. We have 151,200. So as a store manager, you have lots of options right there. All right, guys, hanging in there? We have one last thing that we're going to look at. Now, the number of distinct permutations, it's going to change when we have duplicate objects. Okay, so far everything's been unique. You know, if 8 people are forming a club, those 8 people are all different. If we have 10 different styles of shoes, again, each shoe is going to be different. But let's say we have some duplicate objects in the set that we're choosing from. So what we want to do is go ahead and do n factorial, where n is the number of objects total in the set. And then you're going to divide it by each duplicate object, how many times it occurs, factorial. And you're going to do this for every single letter or every single object in your set. Okay, so it says how many permutations of the name Bob are there? So before we get into the formula, let's just go ahead and draw them out. All right, you can start with the B, and then your other 2 choices are an O and a B. And then you can flip-flop the O and the B. You can have BO. Yeah, it's always a good one. And then you could also start with an O, and then you would have 2 B's. Now notice, because the letter B is the same letter, if I switch these around, those do not count as different arrangements because we can't tell the difference between them. So we expect our answer to only be 3 instead of 3 times 2 times 1. So here's how we're going to do this. First off, determine what your n is. So in BOB, there are 3 letters, so n equals 3. Now you want to identify how many of each letter there are. So there are 2 B's, and there's 1 O. So we're going to set this up now as n factorial over b factorial times o factorial. So we go ahead and just set it up just like this with all the letters. And we get 3 factorial over 2 factorial times 1 factorial. Now you could put this whole thing in your calculator, but when we're doing this, it's going to be easy to simplify. So if we write 3 factorial as 3 times 2 times 1, and then 2 factorial as 2 times 1, and then 1 factorial is just 1. We can do some canceling right here. So the 2 cancels, and we know the 1s don't change our answer, and so we're left with 3 possible arrangements, which is what we expected right here. All right, let's try it again for the word statistics, just so we can cement this concept. Okay, so the first thing we need to find is n, the total number of letters. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, 10 possibilities. Okay, and then I just start with the first letter, S. And I say, how many S's are there? So you just count them. 1, 2, 3. I just cross them off as I go along. When we move on to our next letter, it's a T. I say, how many T's are there? 1, 2, 3. Cross them off as you go. Our next letter is an A. And it looks like we only have one A. Our next letter is an I. And we have 2 I's. And then the last letter is a C. And we have 1 C. Okay. So what we're going to do now is just take n factorial divided by each of these numbers factorial. So 10 factorial divided by 3 factorial times 3 factorial. We're not going to put 1 factorial because it doesn't do anything to our answer. And then 2 factorial. So you only need to work on using the duplicated objects down here. Okay, and you can go ahead and use a calculator to get this. You don't have to write out the whole thing. So let's just give that a try here. So we have 10 math PRB factorial divided by, I'm going to go ahead and put this in parentheses here. So 3 math PRB factorial times 3 math PRB factorial times 2 math PRB factorial, and hit enter. And we get 50,400. That's the end of our lesson. Thanks for watching.